Finally, multiple linear regression with scikit-learn. Import the packages. We've seen the mean absolute error function. Make sure we have the right directories. Import the data, and we are ready to go. Right, here we go. From sklearn linear model, import linear regression. Now instantiate a linear regression class and fit. Well, that shouldn't be hard. Fit x, y. Here we go. It's been fitted. What are we doing here? Well, lm intercept is going to give us the intercept of the model. We can see that. $384,000. It's an array, as we can see quite clearly. It seems like I want it in a list. How about the coefficients attribute? How is that returned? There you are. It's an array. In fact, it seems to be a two-dimensional array. Yep. And we want to flatten it and turn it into a list. Finally, we're going to add those two lists together. So if I look at the two lists together, we have the intercept at the beginning, followed by all the other coefficients. Let's put them in a data frame. I've got a typo there. df should be data frame instead of pd. What does this show? The intercept is 384,000. Lot area has a coefficient of 1. Overall quality has a coefficient of 15,491. You can see these coefficients are very different. They're not really on the same kind of scale. Possibly one reason why some of these coefficients are so big is that some of the variables are correlated with each other. And some of them seem very peculiar. So a full bath in the basement is plus 461, a half bath is minus 5,000. It's a bit difficult to explain these. So what we're going to do is to exclude some of the variables and rerun the model. I'm going to submit this cell here, and then I'm going to go back, just refit from here. Maybe I'll instantiate it again. And now, well, there's a smaller set of variables, and there's still something very funny going on. The coefficient for fireplaces is massive, 15,949. Whereas, for example, the coefficient for ground floor living area is quite small. Why are those coefficients on two such different scales? You might be able to figure it out. We touched on it in a previous notebook. The reason is that the information is on a totally different scale. The information for fireplaces is probably something like 0, 1 or 2, whereas the information for ground floor living area will go from maybe 500 to 20,000. So at the top end, the effect of this square footage might be something like 70 times 20,000, whereas the effect of fireplaces might typically be 1 or 2 times this coefficient. What that means is the size of the coefficient gives us no idea how important that feature really is in the overall prediction. It could well be that living area square foot is much more important in the final prediction than fireplaces, even although its coefficient is much smaller. There's also another problem. The coefficient for living area, for example, is going to change according to whether you measure living area using square foot or, for example, square meters. So what we are going to do now is yet again use the standard scaler to try and get all the features to be comparable. One way of scaling variables would be to find the maximum, find the minimum, and rescale the variable so the maximum is always 1 and the minimum is always 0, and all the other values lie in between 1 and 0. Standard scaler doesn't quite do that. Look it up and see how it works. I'm going to submit that, and then I'm going to go back and instantiate, fit, and now look at the results. Now that's interesting. What you can see now is that the coefficients are more or less of the same type of magnitude, and they probably are reasonably comparable. And we now see that living area coefficient is 34,100, whereas fireplace coefficient is 10,000. So we might reasonably say that living area is more important than fireplaces. Let's have a look at the means and the variances of the scaled features. You can see the means are all 0 and the standard deviation is all 1, and that also means I can't set that question for homework, because now you've seen what standard scaler does. It rescales every variable to have a mean of 0 and a standard deviation of 1. Let's have a look at the graph of the average sale price by living area quantile. This kind of group by is something you've already seen once, and you can see I'm using Q-cut to get the percentiles. I'm not sure that's a very exciting graph, but it kind of makes sense. As the living area increases, the sale price increases. Right, to do, use the predict method of your LM object to predict the linear model for each row of X. Find the mean prediction and compare it to the mean of the target variable. Is it the same? Well, that shouldn't be too hard. LM.predict X, I hope. So capital X is all we need. So the mean predicted should be np.mean of LM_predict, and the mean of y should be np.mean of y. That's not hard. They are the same. Is this surprising? No, this isn't at all surprising. Our model had an intercept for 1, and the intercept is always going to be able to soak up any overall average error, so that the average error is 0. So no, that's really not surprising. Can we replicate a prediction? What's the prediction on the first example? Well, that's what we're trying to replicate. 197,352. The intercept and the coefficients is all that stuff. So let's do a manual prediction. It's going to be the intercept plus the first row of our features matrix, which is going to be x0 dot, so that's a matrix multiplication with the coefficients. For a change, I'm actually not looking at my notes, so if this works it'll be a miracle. No, of course it didn't work. Let's just check what's going on here. What is the dimension of LM coefficient? It's 115. What is the dimension of X? Just 15. X is just 15. I think we're going to have to do this in the the other way around. That's good, it works. And is it right? 197,352, 197,352. So we are able, unsurprisingly, to replicate the predictions from the linear model class. Calculate the mean absolute error of our predictions. Well, Fn MAE, the actuals are y, the predictions, we made them up here somewhere. LMPred. So the average error is $27,000. So when we are predicting house prices, on average we're getting it wrong by $27,000. That's probably not a very good model. If you were to tell an estate agent they could have sold a house for $27,000 more and made all that extra commission, they might not be too happy. So we're going to see over the next few weeks if we can improve this mean absolute error. Is this mean absolute error a good indication of the performance of this model on future data it has not seen yet? Well, I've written the answer. Actually, probably yes, because it's unlikely to be overfitted, but that's a whole story that we haven't really started talking about just yet. Right now, I would say we have no guarantee that this model is any good whatsoever on data that it hasn't seen. We have fitted a model on data, and we've predicted the model on the same data, and unsurprisingly, it's managed to make some kind of prediction, but we have not got the first clue whether this model would perform well on other data. That's it for now, and that's it for week 2. See you next week.